Hello, everyone. Today we're going to talk about one-sided limits. So let's start with a theorem. All right. Our theorem says, suppose that we have a function f. We have a function f. Suppose f is a function and is defined. And let's use an open interval. And then perhaps this open interval contains a point C. It doesn't need to have this point C, but it could have this point C. Then f of x has a limit as x approaches C. Right. So this is one statement of my theorem. And then this is equivalent. So if I use my double arrow like this, I'm saying both of these statements are equivalent. So we have an open interval, perhaps containing a point C. Then I have a limit as x approaches C. This is the same statement as saying that f has a left limit at C and a right limit at C. So it has a left and right limit at C, and they have to be equal. And then one more equivalent statement, if we want to write this more symbolically. So all three of these mean the same exact thing. So if I have the limit as x approaches C from the right of a function f of x is equal to the limit as x approaches C from the left of f of x, then it's equal to the limit existing. So they're all equal. The right limit equals the left limit. That is the limit. So just to see this with maybe some numbers, not fully, we don't even need a function. Let's say I have the limit as x goes to 3 from the right of f of x is 2. The limit as x goes to 3 from the left is equal to 2. So if I know the right limit is 2, the left limit is 2, then I know this is equivalent to saying the limit as x goes to 3 is 2. That's something I might ask you. If the left and the right limit are equal, then that's the limit. Let's say they're not equal. Let's say if we're at 5 from the right, we get 3. And if we're at 5 from the left, then we get, let's say, 2 also. Then we're looking at the limit as x goes to 5 from, just in general, of our function f of x. Then it doesn't exist. They're not equal. So that's what's helpful about this theorem. If I have a right and a left limit, they don't equal each other, as in this case here. These aren't equal. One's 3, one's 2. Then the limit doesn't exist. If they match, and I didn't write f of x here, but that's clear because we don't have a real function. Just saying in general. If they match, that's the limit. They don't match, then it doesn't exist. That's a very helpful theorem. So a lot of times we can look at the left and right limit and tell you something about the limit in general. All right, let's look at this graphically. So let's take a second and draw this graph. So we'll just draw the positive quadrant to make it nice and easy. So let's say we have our positive quadrant. We'll label it to 5, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll have it start at 0, 0. We'll have a little jump here. Say our function looks something like this. Let's find some limits. So let's say we have the limit as x goes to 0 from the right, limit as x goes to 0 from the left, and then the limit as x goes to 0. So we'll look at 0, because 0 is a special case here. We'll look at 1 from all directions. And then let's look at 4. Okay. So let's start at 0. 0 is a unique case since our function starts at 0. So it's not going to exist in one direction because there's nothing to the other side of the function. So when I say left and right limit, what we're going to do is we're going to start somewhere to the right of the function and then approach the point in question. So if I'm approaching 0, I can start anywhere to the right of 0. Let's say here. As I head towards 0, I'm approaching the point 0. So the limit from the right is 0. So pick anywhere to the right when we have the positive, go towards 0, and then whatever the value is that it approaches, it'd be 0. So here I can't approach from the left. There is nothing to the left of 0 in my function. The function starts at 0. So it doesn't exist. But however, the limit is still 0. So this is very important in the theorem. I used the wording open interval. This is allowed to happen in one condition and the limit exists, if we're dealing with an endpoint. If I have an endpoint, the right limit or left limit could exist, and the other one doesn't exist because it's the endpoint. There's nothing to the right or left. So that limit still exists at that point, but that's only allowed to happen if it's where the graph starts or ends. So that's a special little case there. All right, let's try 1. So from 1, I'll use red now. So the limit as x goes to from the right to 1. So I start anywhere on the graph to the right of 1. So this is 1, where I draw in red. I pick anywhere on the graph to the right. So let's pick here. That's on the right. I'm going to approach 1. As I approach 1, I'm thinking, what's the y value? So the x value is 1. This y value is 2. Now from the left, if I pick somewhere to the left, so let's say I start at 0, and then I approach, this is now equal to 1. So from the left, it's equal to 1. These numbers don't match, so the limit does not exist. Take a second and try 4. Right. So now let's look at 4. From the right, pick somewhere to the right of 4. And then we head to this point. So 4 is about 5 from the right. And then if I go from the left now, so somewhere to the left of 4, to the left of x equals 4, the y value, we'll say is about 2.5. You said 2 or 3, doesn't have to be perfect here. That's okay, as long as it's in that range, whatever this point is here. And then they don't match again, so it does not exist. So the point doesn't have to exist for the limit from the right or left to exist. So if I say something like, what is f of 1 or f of 4, meaning what's the value at that point, it's going to be where the closed circle is. So f of 1, I'm saying when the x value is 1, what's the y value? So it would match to where the point actually exists, which would be 2. For f of 4, it'd be where the point exists. The point exists at we called 2.5. So that's going to be it for one-sided limits. Have a great day, everyone.